So our next panel presentation is going to be the University Rover Challenge panel. And it's going to be led by Kevin Sloan, who is the director of the University Rover Challenge at the Mars Society. Welcome, Kevin.
Hey, thank you so much. Glad to be here. Thank you for having me, letting me talk about the incredible work the students are doing. Thank you to everybody helping behind the scenes to run the convention. I know just how much work is going on in the background between James, Carrie, Lucinda, Lee, yourself, a whole host of folks really doing a lot of incredible work to bring the convention to everybody. So pulling up slides right now to share. So along the way, please don't hesitate to ask questions. I love a good interactive presentation, and the questions really make it exciting. You're going to hear a lot of enthusiasm in this presentation because I really get to speak to the passion of hundreds of college students and the work that they are doing, and hopefully that really comes through with the presentation. Now, for those of you who aren't familiar with University Rover Challenge, or URC, may be wondering what it is. Some of you may know a little bit about it. Hopefully the name speaks for itself a little bit. But URC, more than just Mars rovers, URC is challenging. Ask any of the teams, they'll attest to that. It's exciting. Anytime you get this many college students together, you know they're always going to have fun. It's extreme. And I think that just speaks to the incredible environment that we have at the Mars as a research station, and to the tasks that we're able to put in front of the students. But URC, what is URC? University Rover Challenge is the world's premier robotics competition for college students. We task college teams with putting together a multidisciplinary group of students to design and build next generation of Mars rovers that could support astronauts in the field on eventual human missions to Mars. The final competition itself takes place at the Mars Desert Research Station every year. MDRS, it is a tremendous home to host this competition. And the context of everything that happens at MDRS within those simulated human missions is really the perfect sandbox to play in for the rovers, and the perfect place to test out just how a rover could work alongside astronauts. Now, the rovers are not fully autonomous. They are controlled in real time by humans. We're not simulating the delay of a rover being controlled from Earth. When a rover goes and is accompanying a human team on the surface of Mars, that team's going to be able to operate it in real time. And similar to how the EVAs are conducted at MDRS, several astronauts will often be out in the field, but there's usually at least one astronaut who's back in the station. And so the assumption is that astronaut who's back in the hab, or multiple astronauts, could be controlling the rover to extend their presence out into the field. This could be to accomplish mundane tasks, going to service some equipment that happens to be malfunctioning, could be going out conducting some initial exploration, looking for interesting scientific sites before the astronauts head out on a future EVA. It could be supporting the astronauts while they're out exploring. And you'll see that in the competition missions as we dive into those. But at first, I think it's a little bit better we'll take a step back, look at a year in the life of URC. We model the competition on the traditional academic year with a fall semester and a spring semester for those of us in the North Hemisphere. So in late August, early September, when most universities are heading back to school, that's when we release our rules each year. But of course, for a lot of the teams, the planning has started in the months leading up to it. But the rules are released each year, and really the rules stay fairly consistent year to year, but we do like to change things up, give teams a new twist on the competition each year, change up some of the mission tasks, keeps things exciting for the teams, making sure that they're continually having to invent, come up with new solutions to innovative challenges that we're able to throw their way. So teams start working early in their first semester of the academic year. Then in the late October, early November timeframe, we have the registration window. Teams have to register early, and really the main reason that we do that is we want to make sure the teams are committed to this project early on. given the magnitude of what we're asking teams to do, it's not something that can be rushed in a couple of months right before the competition. So we need to be confident that teams have really started work. They've got the resources together in terms of the people, the plan, and that leads into the preliminary design review, which is our first major milestone once the teams are registered. Now we have two major milestones throughout the year, and these are an important part of any project process. Any professional engineer, anybody who's really worked in any type of project setting, it's important to have those incremental milestones to make sure that you're progressing the right way, that you're on track to be successful at the end. So the preliminary design review that we have very early on, despite the name emphasizing preliminary design, we're really looking at the programmatic side of things. We're looking to ensure that, I mentioned resources earlier. Resources are the biggest thing. Do you have the right team members? Have you started to identify potential funding? Do you have facilities where you can conduct the work? Do you have a project management plan? More importantly, do you even know what a project management plan is? And that's something that usually doesn't get emphasized in colleges in the traditional engineering curriculum. It might come up as a short module in a single class that students will have in a freshman seminar. But focusing on these bigger picture project management plans, understanding what it means to put together a schedule, understanding how you're going to integrate across different disciplines, just within the engineering domains, what it takes to build a successful rover. You're bringing expertise in from material science, mechanical engineering, electrical engineering, computer science and engineering, obviously, and a number of other fields that are able to contribute to just what is happening physically with the rover. But then more than that, understanding the rover has to conduct meaningful work in the context of field exploration. So it's important to think about requirements. When we tell teams they're going to be executing a mission, that mission is really providing insight into requirements for the rover. So it gives teams that first opportunity to start to address requirements, understanding how requirements of what they're expected to do into the field translates to system level requirements of what needs to be implemented or executed on their rover. So that's a big focus of the early milestone. Now, each of our milestones are also down selection milestones. We have more teams register than we're able to physically host at the URC finals event. The maximum number of teams that we can host on site is 36. And we've had more than 90 teams register a couple of recent years. So you can see that it's pretty competitive to make it through there. With the first milestone, our goal is to pass teams through that milestone. There are very few teams that don't pass that milestone. And really the only reason we cut a team off there is if we feel that they don't understand what's required to put together a successful project plan. And if we feel like they're not going to get a valuable learning experience out of continued participation over the next couple months. And sometimes that's important for teams that really aren't prepared to tackle a major project like this. Sometimes it's important that they stop their work right there and stop trying to bolt together pieces of aluminum, but really take a year off to study, plan, and prepare. And sometimes that's the best lesson that teams can really get out of it, is knowing that there's a different set of skills, resources that they need to bring to bear on the competition. So moving forward into the next calendar year in early spring, late February, early March, this is really when things get exciting. This is the system acceptance review. The system acceptance review is a step beyond what a traditional critical design review would be. A critical design review isn't a milestone that we grade and evaluate, just what we're able to fit into one calendar year. We can really only fit 2 milestones in there. But at the system acceptance review, teams are expected to be demonstrating physical hardware. We're expecting to see the teams that move beyond the design, they're into the implementation, not just implementation, but integration and testing. And teams submit a written report. They also submit a 5-minute video. Their goal is to show how innovative and creative their rover design is, demonstrate that they really have an understanding for what's required in the different missions for URC, and to demonstrate the reliability, robustness, maturity of their systems to show that they really are worthy of being selected as one of those final 36 teams. Early on in the competition, when the number of teams we were down selecting from, when that was a much smaller number, there was a lot more willingness to pass through, and a lot more ability, frankly, to pass through teams that were not far along in the implementation process, but had great designs accomplished. What's happened is this has turned into an arms race of sorts between the teams, where they realize just how competitive it is to be selected as one of those final 36 teams. So teams are pushing themselves, they're pushing each other further and further, and not necessarily out of direction from us as the judges, but teams that push each other to the point where teams that have highly successful functioning rovers still are having a hard time competing for those final 36 spots. We wish we could invite more than 36 teams, but going out to MDRS in the middle of the desert, there's really just a physics-based limitation on how many people you can bring through and logistically fit through a competition timeline. And then late May, early June, each year, that's when we host the URC finals at MDRS just outside of Hanksville, Utah. In URC finals, that's always an exciting culmination, but of course for the experienced teams that are back year after year, usually starts on their drive home or the trip home from the URC finals, they immediately start talking about the lessons learned. And this is really where you can see the impact of what a competition like this brings to the students, where they're always thinking about the next iteration, the next evolution, how they make themselves better, stronger, more competitive for the next year. So the 4 competition missions, I've talked about these a little bit. There's a science mission, an extreme retrieval and delivery mission, equipment servicing, and autonomous traversal missions. I'll walk through each of those, explain those briefly, give everybody a chance to see what it actually looks like out in the field. Now, those 4 events, we break those up into 3 different sites around where the MDRS campus is. The science mission, this is one of the quieter events, because science, as you would hope, it is a very quiet, deliberate, slow and methodical process. For the science mission, teams are tasked with going out into the field, and there are 5 samples that are placed down in the ground. The samples have different properties. It can be a case where there's extinct life, extant life. It can be an example where there was never any life present at all to begin with. But there's different features from a chemistry, geology, biology standpoint, and all thinking about what implications would be for the search for potential signs of life on Mars. Now here you can get a little bit better look on the right side there. You can see one of our judges who's taking care of the samples in between test runs from the 2 teams. And then on the left, you can see one of the teams whose rover has driven out. And this team, they did a really good job of thinking about how they can actually bring the laboratory out into the field. You can see there's that just kind of simple box that the rover has lowered down onto the soil, so that they've created a nice protected environment where they're not going to be disturbed by the ambient light creeping in. They're not going to be disturbed by wind or any other effects going on. Now, inside that box, we can't see the magic that's happening, but through all of the controls of the rover, working through the camera feeds, the different data feeds that are coming back to the operators, they're looking at the samples, they're collecting samples, analyzing them, in some cases putting them in different solutions to look for different results. The science mission, at the end result of the in-field analysis period, data is coming back virtually to the team members who are nearby but can't visibly see where the rover is working. But based on all that data that gets sent back wirelessly, the team members and the team scientists have to analyze that in a very short period of time. We give them about 15 or 20 minutes to make a quick analysis, and then they have to prepare and present a field briefing to judges on the spot right there. And these are trained scientists with astrobiology backgrounds, and the team members have to present a logical, thorough thought process and analysis of the environment. It's always exciting to see what teams are able to do, because this is really the event where the engineers and scientists have to work together the most. And for many teams of engineers, it's the first time they've had to communicate with science, understand what a science requirement is, and how they can build equipment to meet the demands and expectations of, in this case, what is a customer, albeit an internal customer with the science team. And the science students as well, they have to think about how they can communicate their requirements for what is achievable by the engineering team, what they can actually produce, instrument on a rover, and send out into the field. So the ability for those different disciplines to work together is always exciting to see. Now, moving on to the extreme retrieval and delivery mission. And every time I talk about this, I always get a little bit of a smile, and I think about just how much fun our judges have abusing the teams and their rovers. And there's a reason we put extreme in the title of this mission. This is always the most physically demanding mission that we put the rovers through. There's a great snapshot here of the MDRS campus. Image on the right is looking towards the northeast. Image on the left is looking towards the northwest. So north of MDRS is where we operate. And you can see that great expanse of land on the right there, where there are a lot of undulating hills. There's a lot of rocks, boulders, natural features to work with. And then in the left image there, you can see there's incredibly steep cliffs that are off to the west of the MDRS campus there. And we use all of this terrain, and we make rovers climb just about everything along the way. So the scenario with this mission is that there are astronauts pre-positioned out in the field who need support from a rover. And you can think of it just like an assistant running around, grabbing hammer, delivering it to astronauts, figuring out whatever astronauts need, and delivering equipment to different locations. Now, at the start of the mission, we give teams this nice, easy cartoon drawing right here, and everything looks so easy on this simple sheet of paper here. There are 9 steps. The teams have to drive to different points. At each step, they have to pick something up or drop something off or read instructions that are on a physical sign. But it looks easy when you fit everything onto a single sheet of paper. Everything looks small. But again, if you think back to those last images and you spread this out over a quarter or a half mile across the MDRS campus, it gets to be a pretty big and daunting task quickly. And these are timed missions, so teams are on the clock, they're having to race. If teams are not aggressively driving through each of these tasks, they're going to struggle to get through each of the stages and complete the full mission to score all of the points. So you can see here a rover driving towards a piece of scientific equipment where they had to deliver a payload at one point. In the foreground here, this is actually one of the more exciting features that we like to send teams through each year. This is what's known as the rock garden. And you can see all those rocks that are in a very tight formation. Some of them are slightly level, but with the gaps in between rocks, just the variety you have in that formation there, it's extremely difficult for teams to navigate and drive their rover through there. And so in the previous finals competition, teams had to drive through there, but not just to simply pass through, but to actually accomplish an objective. So you can see here, there's a tennis ball in the image on the right that was marking the location where the rover had to drive up to that vicinity there. There were 3 different rock samples that were placed there. Teams had to have an understanding of different rock types, and they were assigned a specific rock among those 3 that they had to pick up that they would later deliver to that box that you saw in the previous image. Now teams have to do this. You can see just how hard it is to, of course, it's unfortunately not video, just working around some of the zoom limitations, but you can imagine just how difficult it is for a rover to drive over these rocks, many of which are the same size as the wheels on the rovers themselves. And then, of course, when it comes time to pick up the rocks, this is where things really get interesting for teams, and they start to realize that the way they designed and tested the rover may be different than what's required of them in the field. If you think about a team that's working inside a building, building a rover, doing standard laboratory-based testing, anytime you put a manipulator or that robotic arm on a rover, teams are usually going to be practicing with picking up objects that are either directly in front of the rover or might be sitting on the floor. Now the floor obviously is at the same level as the wheels. Now in this picture here, you can see the wheels are slightly elevated because of those rocks, the rocks that they have to drive over, versus the rock samples that they're required to collect. The judges intentionally set those rocks in a depression that is several inches below the wheelbase of the rover. Now the rovers are required to do something that was not necessarily in their design plans, where they actually have to reach below the virtual ground that is their wheelbase and see if they're able to actually accomplish a dexterous task of actually getting their arm down, being able to articulate the wrist at just the right angle to pick up one of those rocks. And really, until you've been out in the field, and this is true across robotics in general, and really all engineering disciplines, this is where you start to discover the differences between your laboratory environment and the real world environment. And so that's a big reason we always stress to teams the need and importance to test in a variety of different conditions. This is just one example of that right here. Now, once teams get through that obstacle, it's on to a series of other objects that have to be retrieved. On the image on the left, those of you with good eyes might be able to detect the rover getting ready to pick up a red water bottle. Now, looking here through a fairly high quality image, it's not too difficult to see that red water bottle. But just remember, teams are viewing this entire landscape and environment through the first person point of view cameras that are embedded on the rover. So they're in a much different perspective. It's really much more akin to almost looking through soda straws. You have a very narrow field of view that you're looking through. You can't see out of your periphery particularly well. And then also with the video cameras that are going to be on the rover, the video quality is not as high because it has to be transmitted back wirelessly in real time. And the cameras are being shaken as the rover is driving across the landscape. So it just makes the situational awareness and ability to perceive the environment that much more difficult for the drivers. Once teams pick up an object such as the water bottle, they have to drive it to an astronaut. Now, if you look at the image on the right there, you can see those small undulating hills that look small in one of my earlier images. Those small undulating hills are actually much larger than the height of the rover. And on that image on the right, there is actually an astronaut hiding. And I'll let everybody look closely for a second and see if you can figure out the astronaut. And I'm gonna see if I can get fancy with the virtual laser pointer here. So anybody who thinks they've figured out the astronaut, it's actually right here, right on the other side of this hill. But of course, anywhere the astronaut was going to be hiding was going to be incredibly difficult for the teams and rovers to pick up. So, you know, the ability to move around the environment quickly, look at different directions on the backside of hills is an important skill for teams operating as well as their rovers. You can see another one of the astronauts who's hiding on the backside of a much larger feature here. This is actually the backside looking south back towards MDRS. So teams have to drive back here. One of the other challenges that we've added in here is teams are starting to get on the edge of where wireless communication line of sight starts to break down. So if teams don't really have a robust wireless communication system, they might get out here and suddenly the rover is stranded simply because it can't talk to the base station. So you can see here delivery of a hammer to the astronaut. You'll notice that all of our astronauts are very sleepy. These are not live astronauts. No test subjects were harmed during URC. But we have the astronaut suits lying down here, and teams are penalized if they drop an object on the astronaut. So the object has to be close enough the astronaut can grab it within about 30 to 40 centimeters. But obviously you don't want to drop it on the astronaut itself. So having some level of precision is incredibly important. And then at the end of the mission, moving towards the highest obstacle here, you can see the rover climbing a smaller ridge. And I mentioned the large cliff faces that are on the west side of MDRS. There are a number of ridge lines that run up them. This is a pretty noteworthy ridge line right here. And you can see an astronaut hiding right up here about halfway up. In previous years, we've sent teams up some steeper ridge lines that had steeper drop-offs on either side. And I think even the judges decided there was a little bit too much robotic carnage in those years. So we tried to come up with a little bit of a safer setup for the astronaut in this particular competition year. With this astronaut, one of the things that was really interesting is teams did not know what package had to be delivered to the astronaut until they drove all the way up to the astronaut the first time to view a sign that the astronaut was holding. That sign could only be viewed from the high side of the rover looking back down. So teams were required to drive all the way up the ridge once, view the sign, drive all the way back down the ridge to find the specific package that was requested, and then head back up the ridge one more time to deliver that package. Only a couple of teams are able to make it through this mission each year and actually deliver the package at the end of the final astronaut within the time constraints. And here we can see the legendary Rover team from Poland was successful in that. They were able to drop it off within the time boundary there. And you can see on the right side from way up high, you can see the gallery of observers way off in the distance and get a perspective of just what the rover has to do to beat it through this mission during the competition time. All right, moving on to our third and final site. So I'm going to talk through two mission tasks here, the equipment servicing mission as well as the autonomous traversal mission. One thing that's unique with these two missions is teams are required to compete in these back-to-back. So teams show up to our north site that is about 1 kilometer north of MDRS. Teams start by competing in equipment servicing. After they finish that task, they have 10 minutes to prepare their rover to start the autonomous traversal mission. So this actually forces teams to have a little bit of a methodical plan for modularity in their rover, so that as teams are adding a manipulator from some tasks, taking it off for others, ensuring that they have the right balance of batteries and power on board, all those different subsystems that they have to think about in balance, having the ability to quickly swap those out in the field and thinking about supportability and serviceability of the systems in the field becomes just another design element that we throw at teams. So teams start with the equipment servicing mission. And you can see our mock lander here. Sometimes we call it the beast because it takes 3 grown adults to lift it. And even then, sometimes we need an extra hand. This is a rather large chunk of metal. It's been built to stand up to wear and tear from the teams over the years. This was graciously built and provided by one of our sponsors, Protocase. But this has withstood a lot of rover crashes over the years. But as teams come up to this, there are 3 different panels where teams have to handle a variety of different operations with their manipulator. And we've thought through everything that you could possibly ask a manipulator to do, everything from gross motions like grabbing, lifting, and carrying, all the way to very fine, delicate, and dexterous motions, such as controlling precision equipment. And you'll see that as we step through the different sides. So the side that you'll see in the right side here, starting at the bottom, there is a red handle down here. This handle pulls out a mock-up piece of computer hardware that has malfunctioned. So teams are required to grab onto this handle and physically pull that piece of equipment out of the lander, separate it. If teams are really successful and ambitious, and we've never had a team successfully complete this next step, it's setting down that the drive they pulled out, picking up the spare that is sitting on the ground, lifting it, and inserting it at the correct angle back into this slot. Now, grabbing it just at this end here, you can think about the torque or moment that's really required by the rover and the amount of precision that's required. We're still waiting for one of the teams to accomplish this specific task. And I know one of the years there's going to be a team that gets there, but that, meeting a milestone like that would be a pretty tremendous advancement, not just in what college teams are able to do with robotics, but really what any organization is able to do with robotics, given the limitations on these rovers. Now, after pulling out and potentially swapping that piece of computer hardware, there is this small joystick right here that teams have to physically grasp. And I should note that everything on this lander was designed for a human to be able to handle and work with their hands, because again, we're in the context of a human crewed mission. So a rover needs to be able to accomplish any of the tasks that a human would be expected to. So in this case, they have to control a joystick that is toggling and adjusting the angles on the satellite up here. Now there are a pair of analog displays right here that are providing readouts of the angles that the satellite is at. So teams have to adjust with the joystick. They have to monitor at the same time while they're adjusting with the joystick. They have to monitor these gauges and dials and ensure that the dials and gauges get to just the right setting, which is provided to the teams. Moving around to the next panel on the left side, you can see a series of button and switches. Teams are required to hit very specific set of those. It's not simply running through and hitting every switch as fast as you can, but having the precision to be able to read the writing that is associated with those, and only hitting select switches, not just randomly hitting all the switches. Then there's a panel access door right here, which is more of a traditional door that swings out to one side. Teams have to be able to grab this latch right here that, again, is designed for human hands and be able to swing that door open. This is not spring loaded. The door does not automatically pop open on its own. Teams and their rovers have to actually have control throughout, pull it the whole way open, and find a way to get their arm out of the way so the arm doesn't actually accidentally bump the door shut when it's coming back around. Once you open that access panel, there is a keyboard and display on the inside, and this is the launch control sequence for the lander, and teams have to enter the password for the launch control sequence, which involves actually going in and precision typing on a standard QWERTY keyboard. Not something that you think of a rover routinely doing, but again, this is equipment designed for humans, where you want to accomplish a task with the rover so that you're not burdening the humans with that job. You can see here a couple examples of teams trying this. On the left is a good example of a team getting ready to pull open that latch, and you can think about the arc that door is going to take as it spins open, and that is not necessarily something that lines up with the geometry of this arm. So there's a very complex kinematic relationship that has to happen there, which is really just the relationship of all the angles of the different joints and how they're going to work together. Very similar to a human arm. We take for granted when we open a door, but we're not thinking about the complex multiple degrees of freedom and the relationship that happens between your wrist, elbow, shoulder, back, hips. Those are all different points of actuation on the human body that help you open a door more efficiently without simply pulling the door open into your face if you're standing in the way. So something that has to actually get implemented with the rovers. And I talked in some of the earlier tasks about what teams are looking at the world through. So here's a team that actually has a fully contained command and control station with several video feeds coming through. That is the only situational awareness that teams have. So if they want to get the context of the full rover, they need to be backed far away, further from where they can actually touch anything on the lander. When they actually move in to perform some of those specific tasks and objectives, they're really narrowed in very close, and it's again difficult to see the proverbial forest through the trees. Sometimes they lose some of that context of what the entire lander looks like. Also, if you just have a single camera pointed forward, you lose that depth of field that as humans we're used to seeing or used to having at our disposal through stereo vision with two eyes looking forward. Looking through a single camera, you lose a little bit of that depth of field. Occasionally, we'll see teams get incredibly innovative. They'll start to look at the shadows that are cast of their rover arm approaching the panel, and they'll start to use that to gain a sense for the depth of field. So there's a lot of ingenuity by the students, not just on the systems that they're building, but also how they're thinking about handling obstacles in the field and dealing with the operations of their rover. Now, one of the last tasks that teams have to do, there's a drawer that pulls out, and there is a small cargo container that teams have to pick up. It's usually sitting off on the side over in the sand. Teams have to go drive, pick it up, and insert it into the drawer. Now, you'll notice if you're looking closely and paying attention, you'll notice that these are two different teams. You can tell a little bit, if you look closely, you can see the rovers are slightly different geometries, but you'll notice a mistake that the team on the left did. And hopefully any teams watching right now will think about how they're actually going through the sequence of events. This was a team that picked up the cargo canister, which takes time, but they picked it up before they opened the drawer. You can see the team here on the right was smart planned ahead, open the drawer before they picked up that cargo canister, their lunch pail, and brought it over. When you're on the clock, it's important to think about the sequence of events to ensure that you're being as efficient as possible. Now, getting that canister down into the drawer is not easy. That's not a big open drawer. We have a slot in here cut out of foam, and there's some nylon that's sticking out a little bit, but it's just air that's creating a little bit of that puff factor you see there. But the foam is cut very precision so that that canister has to be aligned perfectly to slide down into that slot. So not only do teams have to pick up this somewhat heavy box and hold it in the right position, but there are now 3 degrees of rotation that they have to ensure are perfectly aligned at that exact point in space. And so this is really the ultimate 6 degree of freedom problem of what you're controlling at the point of your end effector, which is another way of saying the gripper at the end, and how you're controlling an object to slide down. You can see the team on the right here. They're having a little bit of a success getting it in. Sometimes it takes a little bit of additional nudging. This is the team from Missouri University of Science and Technology. Now, a team that had a little bit more trouble here, you can see their box is actually tipped over on its side. Once the box gets tipped over on its side, it's much more difficult to grab back onto that handle, tip it up the right way. So a lot of times what teams do if they find themselves in this predicament, they start thinking about how they can get the most points the fastest. They know they can simply knock the box back off to the side and move on to the next steps, which include closing the drawer and then securing a fastener right here. So there's a fastener. It is usually either an Allen head or a Phillips head screw that has to get screwed in. Now, we provide teams with the appropriate hand screwdrivers down here so that if they're really feeling bold, or if they're not prepared with the right bit to go in and tighten that screw, they have the option of trying to grab one of those screwdrivers, pulling it out of the slot, and conducting that operation. Not the easiest in the world, and usually teams, what they plan for is they actually integrate 2 different drill bits, both an Allen and a Phillips head, into their end effector. And you can see here with this team, they've actually integrated it into the furthest back joint on their end effector or gripper, and they open their jaw up all the way, and they actually do something with their gripper that I can't do with my hands, but you can see they're articulating the fingers backwards so that it protrudes that bit forward, and that is able to insert and actually tighten that screw all the way. The design on the right here was Stanford University. They were one of the few teams that was actually able to get that screw in all the way. All right, now that competition or that mission ends. 10 minutes later, it's on the autonomous traversal mission. This is the only event where autonomy is actually required on the vehicles. Now, autonomy is when the human takes their hand off of the controller, the joystick, and the rover has to do its own thinking for a period of time to move between different obstacles. This is actually similar to how the current Mars rovers operate right now, where the rovers are sent a task to go between one waypoint and a second waypoint, and they have to determine their own route and navigate there. So for this task, we have a series of visual markers that are placed in the field. In this example, you can see here, there were tennis balls that were placed on stakes out in the field. Those are incremental gates that teams have to drive through. So teams are expected to start at one gate, program in the coordinates of the next gate, and then they're required to enter autonomy mode, where the operators go hands off and the rover has to find its way to that next gate. When the rover believes it has reached a point within 2 meters of that next gate, the rover is required to stop and provide a visual and audible signal to the judges that informs the judges the rover believes it is actually in the correct location. The reason we make teams go through that extra step is you want to hear a positive acknowledgement from the rover that the autonomy believes it has reached a successful end state. Sometimes rovers will be lost going around in the field. A rover won't know where a tennis ball is, but it happens to randomly either pass by or pause for a brief period of time next to a tennis ball, having absolutely no idea the tennis ball is there. So that's why teams have to actually have a rover that acknowledges an understanding of its presence and environment. And it's always frustrating when you can tell that a rover is lost and it can't find the tennis ball. And there's something where you have to have a visual sensor on board to actually detect where that tennis ball is. Sometimes it's just difficult to image that tennis ball in an outdoor environment with a lot of high intensity sunlight. So you'll see rovers driving around in circles, doing different spiral search patterns, looking for the tennis balls. And there have been a number of times where the rover has driven either right by or even run over the tennis ball, never having been able to pick it up in its cameras or detect that it was present in the camera view. Now, it's not always flat terrain. As teams progress further along in the gates, we send them to incredibly difficult terrain to reach tennis balls that might be up higher on ridge lines, where the rover has to have some ability to think about path planning, which is really starting to get into a fairly advanced level of artificial intelligence in path planning that teams are implementing on these rovers. So we're really pushing what teams are able to do. And the progression of technology at URC over the years, we've been able to really leverage and adapt to a lot of advancements in the field of robotics that have happened over a very short time. Now that we've walked through the 4 competition missions, just a chance to look at a couple of systems, note some really unique features, and the ability to point out some trends that we've seen from teams over the years. What teams have been able to think through and implement is exciting. This rover on the left right here, these are very non-traditional wheels, and this is one of the trends that we've recently seen, where teams are starting to use 3D printing or additive manufacturing for the construction of their wheels. Now, one thing that they've been able to do is come up with novel tread designs that are integrated into the rover, or even, as you see, if you look carefully at the kind of the cross section right here, you'll see that it's a lot of open channels. And actually, if you look on the back wheels, it's a little bit easier to see. There are open channels through the cross section of the wheel. And those are a built-in shock absorber. It's an added part of the suspension where you're allowing additional compression within the wheel. So it helps for traction and places less of a burden on, in this case, a rocker bogie suspension the team has implemented. But every little bit of suspension is incredibly helpful as long as it's dialed in correctly for the environment. The team on the right, you can see just some incredible craftsmanship with the robotic arm, and it gives you a sense for a lot of the complexity that goes into a robotic manipulator or arm, because of the fact that so many of your actuating mechanisms and motors are pushed far forward out on what is ultimately a very narrow appendage. So just the ability to run wires and also support the weight of motors out towards the end is one of the challenges teams have to naturally address through this. Here you can see a couple of rovers that have gone for the 6-wheel variation. Now, there's no set rule that teams have to be 4 wheels, 6 wheels. There are no real requirements on the design other than a weight limit. Rovers have to weigh in under 50 kilograms. And we've added a new component to the rules where there's a rover that's being measured right now. You can see a small little box frame. Rovers at the beginning of the task have to be able to fit within a box that is 1.2 meters by 1.2 meters. There's no restriction on the height of the rovers at this point, other than that 1.2 by 1.2 meter box. And this is from one of our previous competitions. Once teams finish their weigh-in and they actually start the mission event, they were able to expand. The rover is able to have a little bit of a larger footprint. This forces teams to think about something that the current Mars rovers have to deal with, of being able to pack into a fairly tight assembly. Now, I mentioned teams don't have to specifically implement a 4-wheel or a 6-wheel rover. And what you see here on the left, this was the first 3-wheeled rover that we've ever seen implemented at MDRS. It was an incredible amount of ingenuity from the team. And I think the judges were incredibly enthusiastic to see teams take that big of a design risk, something that had been never been attempted before by any teams. Now, there's a natural limit to how far you can push the design envelope. We've seen some pretty aggressive designs come in from teams in the past where they perhaps were making a few leaps beyond what physics would allow. So We encourage teams to be creative and innovative with their designs, but at the same time, it has to be grounded in reality, what will actually work. And the 3-wheeled Rover here, this was a case where it was actually something that was viable in the field. Now, that doesn't necessarily mean that we're going to see all teams switch over to a 3-wheel design, but it was definitely exciting to see that creativity. Now, hopefully you've noticed a trend here that a Rover, well, maybe a Rover, not all Rovers are the same. A Rover is a Rover, maybe not. The snapshots on the screen here, so I actually went through the 2020 Rovers that were built, and these were taken from the System Acceptance Review Milestone. And I went through the top 8 scoring teams in the System Acceptance Review for 2020. And if there are any teams out there, any new and aspiring teams that really want to know what is the winning design, is it always a 6-wheel rocker bogie suspension that wins the competition, scores the highest? The answer is no. And so here you have the top 8 scoring teams from the last year's System Acceptance Review. And you can see a lot of different designs. You can see 4-wheel independent suspensions. You can see 4-wheel coupled suspensions. There are 6-wheeled Rovers that are different variations on rocker bogies. A couple of the Rovers have some incredibly innovative suspensions that really don't even fit into the rocker bogie suspension framework. But you can see this Rover up here has a couple of coupled 4-bar linkages that are able to control the vertical deflection of those front 2 wheels. And so just a variety of different ways that you can actually implement suspensions on your Rover and still achieve the desired results. And over the years, we've seen dozens upon dozens of different suspension designs that have been built and tested. And teams are always pushing the bounds of what we assume is feasible with a Rover design. The command and control station, something we talked about earlier. Teams have been moving more and more towards a prefabricated control station that comes in a nice tight box like you see here on the left. Part of that is because teams have a very limited amount of time that they're able to set up once they reach the competition site. So having thought through the command and control isn't something that gets fielded on the Rover, but that is still an essential part of how you're going to operate in the competition. And so thinking through and ensuring that you've got the right tools and your team has an understanding of how to perform is incredibly important. And we've talked about the systems, but the thing that I always love the most about any exciting technology development is not the technology at the end, but it's the people along the way. The Rovers that get built, they're a reflection of the personalities, the creativity, the ingenuity of the students and teams that are building them. And the pictures that we walk away with after URC, you always see tremendous smiles on everyone's faces. You can see the pride. You can see the teamwork, the determination, the enthusiasm. Teams are just putting in incredibly long hours each day leading up to the competition, preparing for this. For many students, it might be their senior design project. This is the culmination of everything that they've been working on throughout their academic career. And now they're out under the hot desert sun with a time limit and a 3-day competition, and just working furiously to get everything to work. But in spite of that competition, the camaraderie between teams, the sportsmanship is always unparalleled. If one team has a breakdown with a part, they don't have the right spares or the right tools, other teams are always at the ready to help provide a spare part if they have it. And in the middle of a competition, to see teams that are willing to offer a lending hand, that are willing to offer a spare part to one of their competitors, just shows you what the competition is about. And competition almost becomes the wrong word at the end of the day. Yes, we do score, and yes, there is a winner, but the teams are just pushing to learn as much and accomplish as much as they possibly can. Getting all the teams together, the ability for students from different schools, different countries, different parts of the world, different backgrounds and cultures, different perspectives on engineering challenges, bringing them all together and letting them compare the culmination of their work over the past year, share design philosophies, understand what worked, what different constraints teams had teams had, just builds to a much broader awareness for all of the teams. And it's always an exciting opportunity. I always start URC each year, and usually by the time we get to the first day of the competition, I'm almost always exhausted. And, you know, on the event management side, the team has always been working hard for the days and weeks leading up to the competition. We're not getting much sleep either. The students aren't getting competition, but they're so young. I've got a few more years added into the fatigue, but I get to the first day of competition, I'm usually exhausted. By the time I get to the last day of competition, after several days of being out under the hot sun for 18 hours a day, working incredibly hard, I'm filled with energy at the end of the competition. And it is all from the students. Just seeing the enthusiasm, excitement, and feeding off of their energy is such a rewarding experience. And it just makes it so much easier to come back each year and try to provide a better experience to the students each year. Because really, that's what this competition is all about. It really is all about that student experience. So just quickly, the evolution of the challenge, we've come a long way. 2007 was our first year. We started the challenge and we didn't really know what to expect. Had an idea for 2 tasks that a rover could perform. We had 5 teams, only a couple of working rovers out in the field, and you can see the winning rover here. And it was exciting at the time because nobody knew what to build for a URC rover. And so there was a lot of exciting work that went into that. But as the years went on and things evolved, you can start to see a progression in the technology. And we got to 2010. This was really the first time that we saw a very mature 6-wheeled rover that started to look more like a traditional Mars rover like we envision in our minds. But as the years went on, get to 2013, a new level of really professionalism started to come into the team's designs and really started to see things take off in the years following that. So 2013, 15 teams. Well, fast forward just 1 year to 2014, we more than doubled that with 31 teams. 2 years after that, more than doubled again, 63 teams in 2016. You can see the size of the competition increasing each year. And this was when we had to start implementing the down selection milestones. 2019, 84 teams in the field. We had more than 500 college students at MDRS. Hanksville, the nearest town to MDRS, is a town of 200 people, and we had 500 college students come in. We had students staying in every direction you can think of, an hour drive north in Green River, an hour drive to the west in Torrey and some of the other communities. And it wasn't just Hanksville hosting us, it was really the entire southern Utah region that has to host this collection of teams and students that are making it in each year. And of course, you can see just the lineup across the bottom of all the different teams. And it's always exciting to see the different flags and all the teams coming together for this one big event at the very end. 2020, 93 teams. Amazingly enough, that wasn't even our highest participation level. 2018, we had 95 teams, but 93 teams in 2020. But 2020, I think, unfortunately, we all know what happened. COVID-19 came up and put a stop on things. So we weren't able to host the finals in person. So I've officially declared this the worst photo ever of a URC finals event. So that's the only way I can describe it. It was certainly a disappointment. But we're not done. We're back for 2021. We don't know everything that's going to happen in the spring, but we're pushing forward with the competition. We're going to continue to reevaluate conditions as we get into the spring. We might have to make some adjustments to what the format of the finals competition looks like, but if nothing else, we've learned from our students. We know that we can adapt to anything. So registration is open now for any prospective teams. You can head over to our website at urc.marssociety.org. Registration is open for about 13 more days until October 28th. So don't hesitate. Before we wrap up, I want to acknowledge and thank our sponsors. We couldn't do what we do without their support. Protocase, a Canadian manufacturing company, they've been with us for a number of years. They've produced a lot of our lander systems that teams operate on. They send out a small army to MDRS each year of volunteers that are working with us out in the desert sun. They provide a lot of custom manufacturing services to students, gives them an opportunity to learn how to interface with professional manufacturing organizations. Microsoft has come along in recent years. They've been a tremendous partner, excited to work with them. And of course, I have to acknowledge and thank the town of Hanksville, the entire community in Utah. They are tremendous hosts to us year after year. We invade the community and they welcome us with open arms. So I'm always incredibly grateful to that community. And of course, just hosting the competition, we can't do what we do without the tremendous executive team and staff members that support me, support the students, and help make this event a reality. So hopefully there are a few of them out there, and really cannot express enough gratitude for everything that they do for the competition. And of course, Shannon Rupert and the MDRS team for helping to host us and be just an instrumental part of what we do.
Kevin, we
now,
have
URC,
about 3 minutes left, just for your awareness.
URC, it's a global revolution. We're going broader, and we've taken over with the Rover Challenge series. Under the Rover Challenge series, we now have the European Rover Challenge, Canadian International Rover Challenge, and the Indian Rover Challenge. Those events have been going on for several years now. European Rover Challenge for quite a number of years, and quite successfully at this point. But all these competitions are building up a lot of global opportunities for the students. So the growth, the hundreds of teams that are able to participate each year, the growth just continues to be tremendous. And finally, before we open it up for questions, I just want to remind everybody, never underestimate the ability of students to change the world. And if there are any questions.
Awesome. Thank you, Kevin. Raphael asks, is there any like that in the Philippines?
So there isn't an event like this in the Philippines. We have never had a team from the Philippines, so certainly encourage you to look into the competition or any of the other competitions that are out there. Indian Rover Challenge might be the closest to you. University Rover Challenge, there's no limitation on teams from the Philippines. So you would certainly be welcome to apply in the future.
With the challenge this year, because they didn't have the MDRS event, was there any other determination of a winning team for that?
For 2020, we did not have an official winner. We published the scores that teams received during the system acceptance review, and the judges spent a lot of time discussing how we were going to handle this. And at the end of the day, we decided we weren't going to announce an official winner. It was really more important to acknowledge the work of all 36 teams that qualified for the finals. That is always a major milestone each year for those 36 teams, and we didn't want to take anything away from what they accomplished just making it to the finals. So that's how we left things for 2020.
How do you think that affected the iterative process, development process for those teams?
That's a concern that we have as judges, and some of the challenges that some university teams are continuing to have in terms of whether or not they're allowed on campus, whether or not lab facilities are physically open. So that's a risk that I think all teams are facing. It's going to impact each team a little bit differently. We tried to get the rules out as early as possible this year to help with that. We kept the mission tasks the exact same this year as last year to help provide for some of that continuity, knowing that some teams probably said goodbye to their Rovers back in March and may not see their Rovers again until early 2021. So we wanted to keep some of that continuity with the structure of the competition for this year, try to help teams out every way that we can.
There are a couple of questions here from people who, it looks like they were participants on some of the teams this year. Kubra asks, are you going to put a webinar up somewhere? It'd be nice to discuss with our teams the details. I think they're asking about, I'm sorry, I'm not sure exactly what they're trying to find out, but was there a webinar that you had mentioned?
So there, with URC, we have a webinar each year, or we have a webinar series each year that are posted online. We have webinars from previous years that you can find either going through the URC website or on the resources page. I think we have a couple linked, or in the URC news, excuse me, if you go back to some of the older announcements. Also, there were a couple of videos that we did over the summer that are on our YouTube channel. So hopefully teams can find those there. If there's a specific topic you want us to cover, don't hesitate to reach out to us.
Excellent. Thank you very much, Kevin. We appreciate that overview of the URC program, and hope to see you back out at MDRS next year.
Thank you so much for having me.